Okay, hello everyone, and welcome to the week number three for the Pro 2003 Material Selection and Design. So the topic two is going to be about the engineering materials and their properties, part two, because we started part two last week, and this is a continuity for the same topic. So once again, we are going to talk about the materials information for design. We said that the engineers need to have a material data if they're going to select appropriate materials when developing a design in general. However, the need for reliable and trustworthy material data tends to encourage the conservative material choices that are going to be limited to well-known and well-tested materials. So the relevant materials data that describe the performance of the materials when applied under the specific circumstances is always going to be required to inform the engineer during the design stage. But what data is sought and where does it comes from? So usually you can see that in this diagram we're going to have the test, we're going to test the data results, get the statistical analysis, list the mechanical properties, make a design guidelines, do the potential applications, and then we're going to do the analysis for the economic and the business cases to find a profitable application. What we need is going to be raw data, which is going to be numbers, some informations, and then we're going to have the knowledge. So all the materials have properties we know that these can be considered as a positive or negative properties, but the collection of the properties for given materials is a property profile. So there are general properties, but most of the properties relate to the specific contexts, which typically relates to the closely to an application. And I think that we did that last week, for example, when we used the software and we found the mechanical properties and general properties, and we tried to actually understand how they're going to be varied and how we can make a selection for the materials based on the application. And we're going to continue with that this week as well. So for example, the graphene is going to have its own properties. Graphene for the materials of the future is a composition, of course, which is going to have one atom thick layer of the carbon atoms tightly fitted together. That's what makes it actually superior. So it's have flexibility, it's have a lightweight, tough, and strong. Conductive, can be biocompatible with the other materials, so non-toxic for the biological cells. Eco-friendly, which can be recycled very easy because it's made of pure carbon, and it's have damp proof, so the ripples, water, and corrosion is going to be limited. But still, you can see that it's a fake news on the graphene. So you can see here that they said that okay, it's not it's a component that causes the COVID-19 vaccines. It's not. Does it have a natural magnetic properties? Is no. Does it become an active with the 5G technology? Is no. And does it actually affect the neutral functions? What neural functions? So actually, all these are fake news. So we have to look at the correct references when we make decisions. So some materials information for design, we're looking at some of the examples here for the material property example. General property is going to be density. We have the price, and we did actually the graph for that, if you remember last week. And just give me 1 second. Yeah. And also we can have the mechanical properties like the elastic modulus. Okay, that's very important thing. Young modulus, shear, bulk modulus, E, G, K, or in gigapascal, the hardness and the toughness. We have thermal properties, which include the heat capacity, thermal expansion, thermal conductivity. And we're going to talk about all this stuff today. Also, we have the electrical properties like the electrical conductivity, which is going to be about how many ohm we have per meter length. So some of the Common mechanical properties going to be the elastic moduli, Young shear bulk, the yield strength, the tensile strength, the compressive strength, the failure strength, the hardness, the elongation, the fatigue endurance, the fracture toughness, the loss coefficient, and the wear rate. And here we have the units for these properties, and some of them actually going to be a unit less. So actually this video, I don't want to play it here, because if we're going to play it here, this will be muted, and thus just check the link yourself. So the mechanical properties, the first one is going to be the stress and strain behavior. Those who done the subject of the automotive manufacturing with me will understand these points, but in general, what you can see is that for any material, we can have a compression and tensile, and from there we can get the properties of the materials under these circumstances. So the applying of the load to a material and measuring the resulting strain provides a lot of the information about the mechanical properties of the material. The most of the typical configuration is going to be a tensile or the tension testing, whereby the tensile load is going to be applied axially to the specially prepared samples, which called the dog bone. Well, of course, it looks like a dog bone. I'm going to have a photo for that very soon. The compression test can also be performed in the same way, but with the sample to be compressed instead of being extended. The shear test and the torsion test are going to be alternate loading configuration that are going to be applicable to the specific applied circumstances. When performing the stress strain test, the relevant standards should always be observed. Once again, the video you can find in the slides are going to be very useful. We're going to watch them. I'm going to add all the links of those videos below in the description box for this video. The stress strain behavior. So that's a sample which we call the dog bone. You can see actually it looks like a dog bone. And well, let me get the laser pointer here. Yep. So what we are going to do is that the output of the tensile test is going to be a plot of the load or the force versus elongation. And that's what we call the stress strain diagram. The results will be specific to the particular geometry of the test specimen. Hence, they need to be normalized to be as following. First, the load is going to be the engineering stress is going to be equal to the force divided by the cross-sectional area of this part. The elongation is going to be the engineering strain, which is going to be calculated by the equation of the strain of the initial length minus final length. Sorry, the final length minus the initial length divided by the initial length, or the delta L change in the length divided by the initial length. So by that, this will be a unit less because it's going to be millimeter over the millimeters. For the stress, it's going to be Newton over meter square, and this will make it in Pascal. So the stress is going to be in Pascal, the F is going to be load in Newton, the AO is the original cross-section area in meter square, the strain is going to be a dimension less, and the Li and the Lo is the length instantaneous and the length original. So the instantaneous length is going to be the actual length at the time that we had the extension force making the elongation for the part. So we can simply plotting the engineering stress with the engineering strain enables the interpretation of the material behavior accepted by the sample, rather than the combination of the material behavior and the material size. So the stress strain diagram will look like the following. As you can see here, we are going to have two stages. We are going to have one before the yield point we call the elastic range. And in this range, we're going to have the modulus of elasticity to control the behavior of the materials according to what we have it known as the Hooke's law. After the yield point, at that point here, everything will be changed. We're going to have the plastic deformation. That means everything we're going to have here is going to be a permanent deformation. Here we're going to have elastic deformation. So by the minute we are going to remove the load, the part will tend to return to its same original position or shape. So the difference between both is that here we just explained actually the yield point, and after the yield point we're going to have the engineering yield, which is going to have engineering yield strength value, which is going to be about 0.2% offset. And at the top here we're going to have the UTS, which is the ultimate tensile strength. And after that the curve will start to drop until we're going to have the fracture. So the fracture is going to be happen, or the breakpoint is going to be happen. We're going to increasing the load to its maximum value. Again, we have a video for true stress and true strain, and in that case we're going to sketch the diagram to have a log diagram instead of having the actual stress and the actual strain. Now we have another property which is called the elastic modulus, and that's the E value we have here. So as seen, when the stress is going to be applied to a material, it will strain. That means it's going to be deformed. As a result, for the stress we're going to apply, under the certain conditions, the amount of the strain is going to be proportional to the amount of the stress. So the highest strain is going to be achieved when we're going to have a higher strain. The part is going to be longer when you're going to add more force to it. So the stress is going to be equal to the elastic modulus multiplied by the strain value. That means that the elastic modulus unit is going to be in Pascal, which is Newton over meter squared, because we said that strain is dimensionless. This is known as the Hooke's law, and it's proportionally between the sigma and the mu, or stress and the strain, is going to be the elastic modulus of the elasticity, which is also known as the Young modulus. So on the stress with strain plot, the elastic modulus is going to be determined by the gradient of the linear region preceding by the elastic limits in this stage here. So the modulus of elasticity is going to be equal to the slope of the curve we have in the elastic range. We can see actually it's going to be equal to the stress change divided by the strain change. This marks the region where any of the deflection accepted by the materials are going to be non-permanent, and this has an important consequences for the design. So usually we design a material either to remain in the elastic region, like for example the suspension for the cars, we have a spring in the system, so actually we need this one not to be permanently deformed, so we need to design the value to have not exceeding the elastic region. While on the other side, if I would like to deform the metal to make something, I need to have the force to be enough to overcome the yield point. So the deformation it's going to be permanent. So these are the elastic or the true yield point, and we can have the modulus of elasticity, where this actually going to be the turning point between the elastic region and the plastic region. So in practical terms, the elastic modulus is going to be a measure of the stiffness. More preciously, it is the measure of the material's ability to resist the change in length. So common associated terms is going to be the Young modulus, which is equivalent to the elastic modulus. We have the bulk modulus, which is a measure of the ability of the materials to resist the change in the volume. So the Young modulus is equivalent to elastic modulus, resistant to change in the length. But for the bulk is going to be change in the volume. For the shear modulus is proportionally between the shear stress and the shear strain. So atomically, the elastic modulus is a measure of the changes in the interatomic spacing between the adjacent atoms and stretching of the interatomic bonds. As such that its elastic modulus tend to be highest for the metals and the ceramics, and polymers tend to be much smaller. So increasing the temperature will simply tend to decrease the elastic modulus for any materials. So the yield point actually is going to be dropped down if the metal is going to be heated up. And that's the reason actually why the blacksmith is heating the metal before he's going to do the forging or making a deformation for the material. So we're talking about the plastic deformation when the material is going to be loaded beyond its elastic limit or the yield point. It will begin to have a permanently deforming, and this involves the breaking and the subsequent reforming of the atomic bonds as the atoms are going to be repositioned. Practically, this means that the material will not return to its original dimensions or shape once the applied load is going to be removed. So the difference between the plastic deformation and the elastic deformation, that in the elastic deformation, the part will return to its original dimensions when the load is going to be removed, while in the plastic deformation, the deformation will be permanent. The inelastic deformation. So within the elastic limits, an assumption is made that an applied stress will lead to an instantaneous resultant strain. This suggests that the maintaining an applied stress will yield a constant strain over the time. So in reality, many engineering materials accept the time-dependent behavior, and this means that the strain may continue despite the constant stress. It can also mean that the recovery of the shape after the removal of the stress can take a finite period of time. The metals will tend to accept a very small inelasticity, but the polymers can accept a lot. So if you remember that we got these results from the software last week, what you can see here, the table number 1 is going to be about room temperature, elastic, and the shear moduli, and the Poisson ratio for the various metal alloys. So we can have the moles of elasticity in both gigapascal or the psi, and the shear modulus in gigapascal and psi, and Poisson ratio, which is unitless. These parameters will be changed if I going to increase the temperature. So you can see here that the moles of elasticity is going to be higher for the tungsten up to 420 when the temperature is going to be negative 200 degree. If I'm going to take it to 0, it's going to be dropped down to 400. If I'm going to start to increase the temperature up to 800 degree, this value will be dropped to 350. That's what we're going in gigapascal. Same thing for the steel, more for the aluminium. So that's what we call actually the thermal stability. Some of the materials are going to have more thermal stability than the others. You can see that the change is going to be highest for the aluminium. Again, this graph is what we got from the diagram from the software directly, so we can simply find what will be the properties of every single metal we have on the periodic table. So we talk about the Poisson ratios now. As already discussed, the application of the stress in given direction results in the a combining of the strain in the same direction. That is, applying the tensile stress in the axial direction of the materials will yield an elongation in the axial direction. That means it's going to be extended. So while the strain occurs in the axial direction, and let's go that this Z direction, so strain Z is going to be applied, constructions of the negative strain will be simply going to be also occurs in the direction perpendicular to the applied stress. And this will be an X and the Y direction for the strain. In general terms, the material gets thinner as it's going to be stretched. And you can tell about that if you're going to get a rubber band and try to stretch it, you can see that it's going to get thinner in diameter. So if the material is going to be isotropic, then the strain in the X and the Y direction will be equal. So the Poisson ratio is a parameter that relates the lateral and the axial strains in the materials as a ratio. So the Poisson ratio is equal to the strain in the x direction divided by the strain in the z direction, or is going to be equal to the strain in the y direction divided by the strain in the z direction. So the following video is going to give you more about the Poisson ratio. So for nearly all materials, that the lateral strains will be in the opposite orientation of the axial strain, and so the Poisson ratio is going to be positive. For purely isotropic materials, the Poisson ratio should be theoretically equal to 0.25, and the maximum is going to be 0.5. And this results when there is a zero net volume change. A typical values of the real material is going to be anything between 0.25 and 0.35. There are many anisotropic materials, and while the lateral strain may still be negative relative to the axial strain, the strains in the x and the y direction can be different due to the reduced crystal symmetry and or the absence of the randomness in the alignments of the grains. There are also a small number of the materials whose specific atomic architecture leads to the lateral strain that are going to be in the same orientation as the axial strain. That is, when they stretch axially, they're also going to be stretched laterally. And these are going to be called the oxidic materials. And that's what we can see here. So when we're going to try to stretch it, the width is going to be dropped. Okay, so we're going to have both orientation strain to be occurred, and that's what we call the oxidic material again. Now, the other property we're going to talk about is going to be yield strength. So, as already discussed, the limits of the elasticity will exist beyond which the material except for the permanent strain, and that we call the plastic deformation. And the point at which this will occur is called the yielding. And the stress at that point is not at the yield stress or the yield strength. Okay, so the point that will represent the turning point between the elastic mode and the plastic mode is called the yield point. So for the with respect of the engineering design, in most of the instance, exceeding the yield strength of the material is going to be undesirable. Hence, the yield strength is going to be commonly considered as a property of consideration. So the yield strength is going to be denoted by sigma y. And note that strength is typically going to be reported over the stress, as strength is going to be considered as a material property and the stress related to the loading situation. You got that? So if I'm going to have a material, it's going to have a property which called the strength of the material. But if I'm going to apply a load over a certain area, I will call it stress. So we're applying stress on the material to have the strength of the material to be tested. So the tensile strength beyond the yield point, we said that additional stress is going to be still required to continue the plasticity deforming the material towards the failure. At some point, a maximum will occur, and this known as the tensile strength or the ultimate tensile strength or the UTS, which is going to be at the top of the curve here. With respect to the engineering design, the tensile strength or the ultimate tensile strength corresponds to the maximum stress that the materials can sustain, which is going to be in tension, due to the effects of the plastic deformation, which is going to have the nicking in the metal when the specimen diameter will be dropped down in a certain point. And stress will become confined to an ever decreasing cross-sectional area, so the failure can occur rapidly. So you can see that the tensile strength here is known as the TS, and the ultimate tensile stress is going to be known as the UTS. Now, another property is ductility. So ductility is a measure of the degree of the plastic deformation that can be sustained at the fracture. So the material that exhibits a low or nil plastic deformation are considered to be brittle. So the good ductile material is the one that can be actually have a plastic deformation to more degree than the less ductile material. While the brittle one that cannot take too much ductile material is going to have fractures. So something like if you're going to have some of the metals like the aluminium, if you try to bend it cold, it will simply fracture. So it's going to have good ductility to a certain limit. While the steel, you can bend it even cold to a very high degree without having the fracture to appear in the upper side, which is because you're going to have compression on one side and tensile on the other side. So ductility can be measured as a percent of the elongation or reduction in the cross-sectional area. So the elongation percent is going to be equal to the final length minus the original length divided by the original length multiplied by 100. And we can see that the highest value for the elongation will mean that the material is more ductile. So that brittle material is going to be simply break at C, but the ductile material will continue all the way to the point C prime. So it's going to take more strain than the brittle material. Some of the material actually going to break at the point A, like the ceramic, have no ductility at all. So design consideration for the ductility is first, extent of deformation, which is going to be strain at the extent deformation strain at the failure, extent to allowable strain during the fabrication, and we have the brittle materials are going to be considered to be having less than 5% fracture strain. So different materials, as we mentioned, is going to have a different ductility percentage. You can see from this table, the brass is going to have 68%, while something like the titanium is going to have 25, the steel have a 25. Different degrees of steel definitely going to have a different percentage of elongation. Once again, the increasing in the temperature will change these parameters. So the highest temperature will cause a further strain percentage. Okay, so the other mechanical properties with tensile property is going to be the resilience. So resilience is the capacity of the material to absorb the energy when it is going to be deformed elastically, and upon the unloading, have the energy recovered. As a material property is referred as a modulus of resilience. So let's have an example on that. The springs. So actually in the spring, you're simply going to make a deformation, elastic deformation, and when you're going to relieve it, it's going to return back to the original shape, either in compression or in tension. It is equivalent to the strain energy per unit volume at the point of the yielding and can be qualitatively identified as the area under the stress strain curve of the yield point. So the resilience or the modulus of the resilience U in joule per meter square is going to be equal to half of the yield stress multiplied by the strain, or is going to be equal to the yield stress squared divided by 2E. Now, the toughness is another property of the mechanical properties of the material, and the toughness has several definitions depending upon the context. So I think that you heard that this is tough material or this is a soft material. So it can be simply an extension of the resilience and defined as the energy absorbed up on the point of the failure. And in this case, it's going to be equivalent to the area under the stress strain curve in general. So just remember that this was for the resilience and this was for the total toughness. There's a toughness test, as you can see in this diagram. You get to have the specimen, you get to have the hammer, hit the part, and see at what extent is going to be bended. So the toughness is also used in the context of the fracture, and so the ability of the material to resist a fracture when a crack is going to be present. The fracture toughness, or the KIC, is another definition. At high strain rates, for example, during an impact, notch toughness is going to be used to assess the ability of the materials to deform rather than fracture. Okay, so that's what's happened, that the hammer will hit it, and we're going to have the notch. This notch is going to tell us exactly what is the ability of the material to deform rather than fracture. Now, once again, these two videos, you can watch them about the crappie impact test and about the ductility, and I'm going to send you the link in the description of the video. Now we're coming to the hardness. We talked about the hardness. We have usually two types of the hardness, which is just a number. It's telling us the highest number, that's means the highest hardness the material will have. And the most common one is going to be the Rockwell hardness. So the hardness is a measure of the material resistance to localized plastic deformation. In early 1800, a hardness was assessed on the basis of one material possessing the ability to scratch another, and that's what we call the Mohs scale. It is scored the materials from 1 to 10 with a torque measure of measuring 1 and the diamond to be measured at 10. Okay, now that's been the chalk, which is the talc, sorry, was going to be very fine material, have no toughness, is going to have the value of 1, while the hardest material at that time, which was the diamond, is measured at 10, and every different materials is going to have the scale in between. Several more quantitative evaluation methods have since been developed, and these involve the identifications of the materials by the indicator of the specific geometry applied at a particular load and loading rates. And the outcome is a value that enables the comparison to other materials. So comparing the results across the different test methods must be done with caution. The hardness testing is important for material performance evaluation due to, first, the indentation testing is usually going to be simple and inexpensive, and can often be applied to the finished components. The hardness testing, which is non-destructive, also can be applied, and we have the it is non-destructive. That means we don't have to break the material to make the test, just applying the force using the tool on a certain position and see how hard the material is. So just try to imagine something like you're going to bring your the pen and you put it on the table and try to push the table with that pen. And if you're going to have an indentation to be appeared on this table, the depth of it is going to be compared to the force that you applied, and you're going to say, okay, now that's the amount of the hardness that this material possesses. Several other mechanical properties also can be deducted from the hardness test data, since both the hardness and the tensile strength are measures of the resistance of the plastic deformation, and they tend to be proportional. So these are some of the mechanical properties of the hardness test procedure. We can see that we have two different methods. The Brinell test is the most common one, by having a sphere, and we're going to actually push that sphere over the surface of the material and check what will be the indentation we're going to have. So you can see that this will be diameter of the indentation that we have on the materials, and this is diameter of the spherical shape itself. And then we're going to use this equation, the diameters for the sphere, diameter of the indentations, and the pressure value. So at the end, we're going to have the value to be a unitless number, and we can use that for make a comparison between the different materials. Also, we can have the vigorous micro hardness by using the diamond pyramids, doing the same things. We're going to have the dimensions for the diamond shape. And once again, we're going to have some indentation to be happened. Then we're going to choose the equation for the HP value to tell how hard the materials is based on the vigorous process. We have the new micro hardness, and we have the Rockwell and the superficial Rockwell process. So you can see that the similarity between the Rockwell and the superficial Rockwell mainly is going to be similar to the Brunel test. So once again, the Rockwell hardness test can be checked in this video, and you can watch it yourself. So these are some of the hardness measurements for different materials based on the different references. So that's, for example, what we have for the Brunel hardness. It's going to be anything between 5 to 10,000. For the Rockwell, it's going to be anything from 0 to 110. Rockwell C, which is using the spherical shapes, 0 to 80. The noob hardness, the bigger hardness range, and we have the mostly is going to be for the most hardness from 1 to 10, as we mentioned earlier, and all the other materials will be distributed in between. So once again, this is the relation between the tensile strength and the Brunel hardness number. The harder the material is, the higher tensile strength is going to possess. So the summary for the mechanical properties are: we have the modulus of elasticity, which is the stiffness resistance to the elastic deformation. The yield strength, or the sigma y, is the measure of the resistance to the plastic deformation. The tensile strength, Ts, is the maximum load bearing capacity. The ductility is the degree of the plastic deformation at the fracture. And the modulus of resilience is the energy absorption for the elastic deformation, while the toughness is the energy absorption for the plastic deformation. And finally, the hardness is going to be resistant to a localized surface deformation. Now, another property that the material possesses is the thermal properties. So the thermal property is one of which refers to the specific response by the material to the application of the heat. So due to their common relevance to the engineering design and the material selection, this section will focus on the heat capacity, the thermal expansion, and the thermal conductivity. So we start to talk first about the thermal or the heat capacity. The heat capacity is the measure of the material ability to absorb the heat from the external surrounding. And by definition, the heat capacity is the amount of the energy required to raise the temperature of the material by 1 degree Kelvin. So the C is going to be change in the energy absorbed divided by the change in the temperature. And we're going to have the heat capacity is going to be in joule per Kelvin mole. Now the thermal expansion, and I think that most of you know about that. Something like when you're going to have metal to be heated up, of course, going to be changed its length. So the thermal expansion occurs in most of the solid materials when they are going to be heated, and conversely, most of the material will contract when they are going to be cooled. The convenient measure of the thermal expansion is going to be the linear or the volume coefficient of the thermal expansion. So the alpha multiplied by delta T is going to be equal to change in the length divided by the original length. In the case of the volume, we're going to have the volumetric coefficient of the thermal expansion. So the volume itself is going to be expanded not only linearly but also in 3 dimensions. So the volumetric coefficient of the thermal expansion is going to be once again equal to the change in the volume divided by the original volume. And this will be equal to the alpha multiplied by the delta T. So delta D is going to be mainly in degree or Kelvin, and the volume is going to be in cubic meter. So this is going to be a unit less, and this will tell me that the value I'm going to have here is going to be in how much degree, per degree, sorry. So the thermal expansion is mainly caused by the increase in the average interatomic spacing between the atoms due to the increasing amplitude of the lattice vibrations, which mainly going to mean the increase of the absorbed energy. So as you can see in this diagram, when I'm going to add the heat, the movement of the atoms is going to be much faster, so they're pushing away each other and it's going to have the expansion to occur. Or we can say that since the potential energy trough is going to be asymmetric, the spacing between the atoms will increases with the increased energy. Additionally, when the bonding energy is going to be high, the potential energy trough tends to be deeper and narrower. Hence, the change in the atomic spacing is proportional less for the same amount of the energy absorbed. And in this manner, the ceramic and the glasses tend to have a smaller alpha than the metals. The high presence of the secondary bonds in the polymers will lead to the corresponding tendency for the very high alpha value. Now, the other thermal property is the thermal conductivity, which is a phenomenon of the heat transport where the heat moves from the region of relatively high temperature to a relatively low temperature in a material. The driving force of the thermal conductivity is the thermal gradient. So the heat flux is going to be equal to negative K multiplied by delta T divided by the delta X, where the Q is the amount of heat to be transferred, the K is the thermal conductivity value, the delta T to the delta X is the thermal gradient, or the change in temperature over the length of the material. The thermal conductivity originates from the migration of the energy due to first the lattice vibration, or what known as the phonons, and the motion of the free electrons. The abundance of the free electrons in the metals means that the thermal conductivity via free electrons is going to be the dominated transport mechanism. But the thermal conductivity in pure metals typically will exceed that of the alloys due to the increase in impurity scattering effects. In ceramic and glasses, the thermal conductivity is dominated by the phonons due to the absence of the free electrons. This generally going to reduce the thermal conductivity overall compared with the metals. As the temperature increases, the phonons actually going to scattering and also increases, meaning that the thermal conductivity tends to decrease. The porosity in the ceramic has a large impact on the thermal conductivity behavior. In polymers, the thermal conductivity occurs via the motion of the molecules, which is going to be typically poor. And the extent of the crystallinity is as important as an increased crystallinity favor for the value for the thermal conductivity. So we come back once again to the thermal conductivity graph. So you can see here for the composition for the W, T, and the zinc, you can see that the thermal conductivity will be increased depending on the compositions of the alloy. Usually the pure alloy is going to have better thermal conductivity. So the pure metal have higher conductivity than the alloys. And temperature, once again, we said is going to be affecting the conductivity. As the temperature will be increasing, the thermal conductivity will also going to be decreasing, and that's related to the something like the observability of the material for the heat. Again, these are some of the another thermal property which is going to be about the thermal shock. If I going to simply give you an idea about that, Just imagine that you have a hot glass and you're going to drop some cold water on it. It will crack. Same thing can be happen for the metals. Okay, anyway, the video will explain anything for you, explain that for you, and I would like you to discuss the explanation about this, about what happened in the class. So the other property is going to be the electrical properties, which mainly going to be the electrical conductivity. So as the material can conduct the heat, it can also conduct the electricity. So electrical conductivity is used to specify the ability of the material to conduct electricity. It originates from the Ohm's law and is the inverse of resistivity. So the voltage or the applied voltage according to the Ohm's law is going to be equal to the resulting current due to the applied voltage multiplied by the resistance. The rho is the resistivity of the material in ohm meter. And the A is going to be cross-sectional area in that equation, and the L is the length of the specimen. The sigma is the electrical conductivity, or 1 over the rho. So the electrical conductivity is specifically the net conductivity of first an electronic component, which charge transport by the electrons and the electron holes, and an ionic component, which is the charge transport by ions. The metals accept a high electrical conductivity due to the abundance of the free electrons. As the temperature is going to be increases, the electrical conductivity will tend to decrease. For the ceramics and the glasses, accept a broad range of the electrical conductivity due to large variations in the electronic and ionic contributions, and their complex relations shifts with the temperatures. So the semiconductors typically fall into this category. For the polymers, typically have a very poor electrical conductivity due to the absence of the free electrons due to the strongly covalent bonds. And in certain cases, some of the polymers can be made to conduct at magnitude comparable to the metals. So the model summary is that the model learning outcomes where the student become familiar with the common material properties affecting the material selection. So now you'll know that you can select the material based on the mechanical properties, thermal properties, or the electrical properties, or all. Also, the important reading and the references can be found from the Callister and Routledge, that the Callister's Material Science and the Engineering for the chapter 6, 18, and 19. Also for the Ashbay, Material Selection in the Mechanical Design, the 5th edition, and this will be included in the chapter 2. Finally, you can watch this video once again, and we can have a discussion about them in the class when we're going to meet you. Thank you very much for your watching, and hope to see you soon. Have a nice weekend, and see you soon.